So this next bit, I'm just going to talk about quantum simulations I've been up to lately in the context of trapped ions, which is not really an introduction, but I hope from the first introductory part we can work together. Somebody mentioned that, oh, I felt like this part was a little too fast during the coffee break, which I love that kind of criticism. So if I'm going too fast, just be like, hey, you're going too fast, slow down, talk to me more about whatever. Like I always say, I've seen all these slides. If I get through 2, I'm as happy as if I get through 10 to me. I'm here to teach you what you need to learn. Okay, so I just want to start off with what does a quantum computer look like? And this is the first fictitious image of a quantum computer that I know of, which is from a comic book series called Planetary. I really like this storyline. The storyline is, of course, during World War II, the British had secret regular computers, which they destroyed at the end of World War II to keep that secret. So in this comic book, the idea is that superheroes had secret quantum computers, basically. And this is what it looked like. Obviously not like anything, giant snowflake. I think it's supposed to represent this many-dimensional manifold of string theory. I think that's what it's supposed to represent. Now, most of the time, when you go to quantum computing images, you'll see one of these chandeliers from a dilution refrigerator. And actually, the thing which kills me is sometimes I will have a press release about my work at Duke, where we work on ions, and somehow the press picture will still be a superconducting chandelier. And it's like, okay, thanks, guys, thanks. I will still stand by that I think superconductors and ions still have done the most complicated quantum computation so far, though of course other platforms are building up quickly. I also mentioned, of course, there are all of these companies, and as I mentioned at the start of my first talk, I'm a conflicted person, so don't trust me on anything. But we're going to be using these atomic ions. These ions all sit in tiny, tiny center here. They're just blown up. This is an example of this bow tie trap from Sandia we'll look at again. They're built in these nice optical systems. So when you think about qubits, I like to split them up into natural and synthetic. So what's nice about natural qubits is that every qubit's the same by nature. If I get a jar of calcium here or in Nairobi, same calcium. They usually have weak coupling to the environment, but that often leads to a challenge in control and putting them together. So actually with Hartmut, who is one of the organizers of this winter school, he and I wrote this paper about kind of our dream ion traps. If there were no materials challenges, if you could add all these detectors, et cetera, what would we really love to see? So if you have material science friends who can solve this problem for me, please send them this way. On the other hand, we have synthetic qubits, where every qubit's up to the same up to some manufacturing defects. They have this stronger coupling to the environment, and they're able to print as many as you can fit on a chip. Now this is actually from HRL, and actually so there's a guy at HRL named Thaddeus Ladd, who I've known since we were both grad students a long time ago. And I always tease Thaddeus and say, I don't know why you only want to print 6. You can print as many as you want, but you've only printed 6. But this is beautiful, beautiful work. But here I thought 2 to me really nice examples of these 2 ideas. So in this recent work from Harvard Kerr, MIT, UMD collaboration, they moved to these neutral atoms. And the beautiful thing about this experiment to me is that it shows that every atom is the same. So even though I want to do 2 qubit gates on all of these pairs of atoms, I just apply one control. And maybe from a computer science perspective, it's basically like a SIMD architecture. So I just do all this simultaneous instruction at once. And that's amazing. And it's only possible because they are the same by nature. Like it's hard, well, yeah, it's hard to get the tolerances that good. On this picture, which is just a example of an IBM layout, and I don't have the really cool thing in this is they print it. There's some small defects. They actually go through with a laser and slightly tune it. And that laser allows them to make the amount of defects way smaller. So like I have no, humans are very ingenious, and I have no doubt that we can make these things more and more the same and reliable and really take advantage of printing. Nature is nice because things are the same. Okay, so what about ions? So this is a picture of ytterbium ions. Each of these pixels here, this set of pixels is one atom. It turns out that the atomic ions we pick, if you shine a laser on them, they glow so brightly that actually barium, it's not even on this list, anyway, barium actually glows a green color. And you, with like a Sherlock Holmes magnifying glass, can see one barium ion with your eye, which is crazy but true. It's just how bright they are. Now, ytterbium, unfortunately, is ultraviolet. And so you can see this on a camera, no problem, but you yourself will never see it. You can pick, we basically, I think this part's really important, which is we don't randomly go to nature and say, give me an ion. We pick very specific ions that are easy to control, easy to prepare, and easy to read out. And what we see in this paper is a really nice summary from 7 years ago now. Already there's single qubit gate fidelities of 6 nines, 3 nines, 4 nines, 2 qubit fidelities, qubit fidelities between different species. And people have different favorite ions, but it's mostly, it's no ion has everything you want. So it's some combination of history and you're making a choice about trade-offs. And so we use ytterbium ions in the experiments I'm going to talk to you about. I'll tell you why ytterbium is good. And I will tell you right now why ytterbium is bad, which is that working with ultraviolet light is no fun. And ytterbium ultraviolet light is way better than working with the ytterbium ultraviolet light you need for things like beryllium. Calcium, which is also commonly used, is much nicer because you can use more visible light. So this is just my cartoon, again, from this Nature Review Materials with Hartmut. And John Chiaverini and Jeremy Sage. And the basic idea is you pick some levels inside this atom that are easy to control as the qubit. And then you have some other level which allows you to scatter a lot of photons. And that scattering a lot of photons allows you to do cooling, it allows you to do detection. And then the conditional operation between these two ions happens due to basically the Coulomb interaction between the charge. So you need a way to somehow transfer information from the ion's internal state onto the charge. So I got this nice video from Chris Monroe, who got it from IonQ, I think. So the idea is we send in this laser beam, we split it into these 32 lasers, basically. And then the way the circuit works is you start by shining a laser which initializes everything into 0. And that's super good. That's like 10 to the minus 6. Then when you do a 2-qubit gate, you'll see the ions move a little bit. And that move, that moving basically is trying to capture the fact that I need to interact with the Coulomb interaction. Single qubit gates are just single lasers. And then at the end, in this case where there's no mid-circuit measurement, you just measure the whole thing. You get a bunch of bright spots, which are 1s, and dark spots, which are 0, and you read out the classical data. This part, I think, is also, I just want to emphasize that at the end of the day, in these ion-trapped quantum computers and quantum simulators, the thing we measure at the end is whether the ion is bright or dark. Anything else we measure is an interpretation of a string of zeros and ones, right? Strings of bright and dark objects. All right. So we use ytterbium, and this is not a summer school in atomic physics, but the key point is that these two ground state here are first order insensitive to magnetic field. So it makes the Z error not that important. And then to drive it in a way where we can actually push the ions around, we use a Raman transition, which shines the same laser, which is basically at 355 nanometers. But we use a pulse laser to span this, the hyperfine structure here. Now, this laser is far off resonant from any, far off resonant from any of these different structures here. Let me turn on this way. Okay, good. Yeah. And what's just a lucky break is that this laser is at 355 nanometers. Turns out 355 nanometers is the same color of light they use to cut the masks that make regular computer chips in all of your regular computers. That makes that laser a commodity, and like you just buy it super cheaply. And then actually, this fancy optics here thing, which splits into 32 things, is expensive for sure, but it's something they make all the time to print, to basically, print more computer chips faster and faster. So it's that's a nice break, and that's not on purpose. That's just a lucky break. And this is an example of one of our chambers. There's the cryogenic chamber over here, and then this is that's the laser there. And what's cool about it is you can tell that it's just for industrial use because there's no labels, just a silver box, has a key. All right, yes?
How do you get the ions to sit, behave so well and sit in this line without moving?
Yeah. So the ions repel each other, so that spreads them out. And then the trap, there's two parts to the trap. So along the axis of the ions, there's just a regular potential. And so the ions don't want to go to the positive walls. And then on the other order, it's a little bit funny because you can't have a static potential that traps charge. So you have these oscillating RF field. But that tightly basically confines it, I think of it basically confines it in a pipe. So these ions are in the pipe, and then they want to get away from each other, and that pushes them into a line. There's been some really cool work from Luming Duan's group in China, where he's put thousands of ions in. And if you put thousands of ions in, they have to spread out in the other dimension. And he makes these kind of 1,000 of ions, they look like footballs, basically.
How do you move ions?
So these trap electrodes here, they're different DC voltages. And so basically, this trap, you could imagine, is made by grounding these, that's a cartoon, of course, grounding these two electrodes, and then making these two positive voltage. And then if I want to shuttle them, like Quantinuum's done a great job showing how to do this, is you basically lower this voltage, start to raise this voltage, and just walk it down.
But it can pass by another ion without the problem?
No, so the ions are in the same trap. They will stay in their order. People have methods to rotate the chain. So you can actually tilt it around so they're on opposite sides. But you can't pass them through each other because the Coulombic repulsion is so strong.
I see. But in the animation you seem to have two ions which are far away. They can have some interactions.
That's right. So that's because they're all, let me get to the next slide, but they're all in the same trap. And we'll see why that interaction happens.
Okay, they need to move them. Okay.
So if this is a chain of atoms, how do phonons interact with the system? Do they play a big role?
Perfect. Yes. Yes, perfect. Yes, great. So the reason why we can have distant ions in the same chain talk to each other is these phonons. So if I try to drive the atomic ion directly at resonance, this shows the resonance of flipping 0 to 1. This is for calcium from the Innsbruck group. You see this. But because the ions are all repelling each other and they're in the same trap, what's important is the collective motion of them moving together dynamically. And if you have n ions, you'll actually have n degrees of collective motion. Now, normally, because of your laser geometry, you will only see probably n of them. Maybe you see 2n. In this example, they're looking at the motion along the pipe, which we call axial motion. And you see all of these peaks are different types of phonons. And so when you're hot, meaning like 100 millikelvin, you see all of these motions, the blue sideband you can think of as I borrow energy from the phonons to make the spin flip. And, sorry, the other way around. Red sideband, I borrow motion from the energy to make the spin flip. Blue sideband, I make the spin flip and I add a phonon. So what's nice is we can do ground state cooling and basically remove all the phonons. And you can tell because all these red sidebands go away. There's no phonon to borrow the energy from. Yeah.
Does that mean you cannot have local interactions between the ions because you're looking at collective excitations, so there's no way to control maybe JFT or something?
Yeah, so that's a great question, which is there's the collective excitations talk to everything. But what helps us is, sorry, I was just seeing if I had an easy figure right here, which I did not have. What helps us is that laser only talks to the ion we talk to. So so it's easiest to think about the center of mass. So in the center of mass mode, axially, all the ions move together with the same coefficient, which means they all couple equally to that mode. Now we'll see in the next slide, but I apply 2 lasers to those 2 ions, and then those are the only ions that will interact. The internal states will interact. Because without the laser, the internal states don't talk to each other. And so that means, and that's the crazy thing about a single chain of ions, is you can do a 2-qubit gate between any pair at the same speed. And I think a lot of times when I say condensed matter physics friends look at it, they think, oh, this ion talking to this ion should take way longer. But no, and it's basically because the speed of the gate is way slower than the speed of light. And the Coulombic repulsion, which that's the normal mode, that's like a speed of light kind of interaction.
And with regards to the relative heights between dredging these sidebands, is that I can imagine that even if you have perfectly coupled like subharmonic oscillators, then maybe it is like different modes or something. But
yeah, well,
limited by your track geometry or interactions there.
So it's going to depend on the structure of the normal mode, which we'll look in that in a second. And then this, for the hot case, it also depends on how well the different modes are cooled. So some modes will be cooled more or less, which will also change the height.
Oh, I see.
Good, good. So here's a cartoon of, so the way we do 2-qubit gates is we want to create this spin-spin interaction, which we usually say is XX. And the way we do it is we typically do something called the Mormor-Sorensen gate. At the time, there were similar ideas from Solano and Milburn separately. There were like 3 gates that are all basically the same idea. So what happens is you go up on this red sideband, so you should remove a phonon, but you don't do it resonantly. You're a little bit short. And then you apply this blue laser, blue sideband laser, which takes you to up, up goes to down, down, and the number of motional quanta is the same top and bottom. Now, because of these 4 interfering pathways, the dependence on the number goes away. And that vanishing of dependence on the number was super important. So the original idea for doing a 2-qubit gate with ion traps is called Tourette-Zoller. It only works if you're in n equals 0. And so this gate was like, actually, we don't have to cool all the way to n equals 0. We can take a little bit of n, it's fine. And of course, it was implemented way before Tourette-Zoller was eventually implemented because it was just a better idea. And then this is my, just soapboxing as always. So I think to me the thing which is interesting about quantum computing technologies is the problem is often the 2-qubit gate. And so the ion traps, they had different ideas for 2-qubit gates. And then everybody agreed on Mormor-Sorensen. And then there's this explosion of activity because the gate works. You see the same thing in superconductors where somehow this, not particularly the gate, but this agreement on the transmon being like a good way to put things together, there's like the explosion activity. We see it right now with the neutral atoms. There's a gate called the Hannes-Pichler gate. So the old neutral atom 2-qubit gate was not that good. And that Hannes-Pichler gate somehow solved that problem. And then suddenly there's an explosion activity. So when I think that's what's great about science is like even if your competitor comes up with the better idea, if it's good, you will adopt it because you're trying to get science done, right? That's it. All right. So for us, we usually use the radial modes of motion. And so in the radial modes of motion, the normal modes, the center mass mode is actually the highest energy mode. And then you can see, to your question about participation, these ions will have different participation in these different modes. And we'll see later when we do our quantum simulation that we're going to take advantage of the fact that this one doesn't participate in mode 2 and 4. So now, next slide, I'm going to talk about the kind of, I say, modern way to think about the Mormor-Sorensen gate. So the left side is nice, kind of pictorial, very atomic physics. There's virtual modes, interference, this kind of thing. But in the modern way, you just write down this Hamiltonian. So there's a spin-dependent term, x on ion I. It has a coefficient, eta ik, which captures how much that ion participates in mode k. It has the mode k, which will have different frequencies. And then we have a bunch of things that we can control, as always. So we can control the Rabi frequency, which is basically the laser intensity. And then we can control the detuning, which we capture as this integrated data. Now this Hamiltonian actually has a very boring commutator structure. It has a very boring commutator structure because x commutes with x, so nothing happens on the spin side. And then this part, these creation annihilation operators, or you can think of it as a sum of position and momentum. In quantum mechanics, position and momentum don't commute, but of course they only give you a number, which means when I think about when I think about the Lie algebra of all the nested commutators, it just stops. Just stops at the first commutator. And there's a way to expand these time-dependent Hamiltonians called the Magnus expansion, which is basically an expansion along commutators. And the Magnus expansion here is perfect because it just stops at second order. So there are only 2 terms. This first term is basically a spin-dependent push. And it's either a push in momentum or position. And the second term is this spin-spin coupling we want. And so then all we do is we just solve by tuning our laser intensity or our frequency so that this guy goes to 0 because we don't want that to kick, and this guy goes to the angle we want for the 2-qubit gate. So in my lab, working with Jung-San Kim, so my lab developed these frequency modulated gates. This is an example of a frequency modulated gate. We implemented it with Jung-San Kim on his experiment. We just did, it's not continuous, just piecewise frequency modulation. These are the 4 radial modes in this case. This phase displacement, this area, ends up being the area which generates the 2-qubit gate angle. And then we go back to the center because we don't want to have any entanglement between the ion and the motion. And then here's, we do some experiments to try to calculate the fidelity. We get a fidelity of about 99.5% in this particular experiment. We're limited in this case by the first laser dephasing, which we made better, and then the motional dephasing, which is just how good is the oscillator. And so we continue along those lines. So for most ion trap quantum computers, the gate set is basically this Z angles. These are basically perfect because they only depend on basically how good your clock is. And we have very good clocks. Actually, I think human beings, probably atomic clocks is the most precise thing we've ever built. We don't use the best atomic clocks, but we use atomic clocks that are so good they're not the problem. These XY angles, again, come through this interaction picture of driving this qubit. This I just showed you with the Mulmer-Sorensen, and then we measure and prepare in Z. So they're kind of cool test beds. Sandia has a Q-Scout test bed you can apply to. I'll talk at the end just briefly. We're building like a giant academic quantum computer, hopefully by 2030 is the goal. We have some quantum computers now you could use. There are all these companies, and there's different language support. So one chamber we have, which is a room temperature chamber, has this, as we call it the red chamber. It's sort of funny because, I see, yeah. No, I lost it. All right, it's fine. We call it the red chamber because actually because the screwdrivers used to have red handles. But then afterwards, we named all the chambers after colors. It's neat in that the way we do addressing is we have these micromirror lens that my colleague Jung-San Kim really specialized in, which allows us to put 2 beams on any of these 2 ions in this plane. Somebody at the end of last lecture said, why don't you just modify the Hamiltonian by having these different controls? And I love it. It's great. In practice, you're just limited experimentally somehow. So in our experiments that have the 32-channel AOM, we can actually individually control 32 ions at the same time. And this experiment, we can individually control any ion, but we can only talk to 2 at once. And it's one of the great gaps between theory and experiment. In principle, it's no big deal to put down 32 mirrors here. But in practice, that's an expensive fabrication process. You have to get right all these things. Perhaps later. The other thing which is neat about this one is because the laser beams come at this 90-degree angle, we can actually talk to all 4 components of the hyperfine manifold. And if I have a laser beam that only goes directly across, I'm only going to be able to talk to 2, basically. And too many details. All right. So what I want to talk about in the next few slides is show you a little bit about how many of these things I talked about with control can actually be applied in the context of quantum computing. So we've been really working on these overcoming different systematic errors. I already mentioned this 2-qubit gate thing. We can do basically a type of decoupling which leads to, allows us to get rid of the motional dephasing by basically looking at the spectrum of what that motional noise looks like. And then we can actually also remove crosstalk by modulating how these different lasers interact on these pieces. I'm not going to talk about all of those things. What I want to talk about is my maybe, I don't know. Sorry, what I want to talk about is what's weird to me about quantum computing is all of our discrete gates, our most famous ones, are Hermitian and unitary. And we have Hadamards, Polys, C-naughts, Control-Control-Z, Control-Control-X. And it's weird because most unitaries are not Hermitian. So now let's say I want to apply the Hadamard gate. I don't have a Hadamard button in the lab. What I have is X rotations and Y rotations. So if I want to do Hadamard, I have to do an X rotation followed by a Y rotation. But then, because of what we talked about, there are like multiple paths through Hamiltonian space that lead to the same unitary. I have a choice of which way I do it. And what we see is both the red circuit up top and the blue circuit below are both Hadamards. But if I take the complex conjugate of the red circuit, I get the blue circuit. So one is kind of Hadamard, and the other one is kind of Hadamard dagger. And in some sense, that's like nonsense because Hadamard dagger is Hadamard. But we'll see it has some real operational meaning. Similarly, when I think about this common circuit, which I'm probably not going to do because RZ theta is better by itself, but I apply Hadamard Rx theta Hadamard. And when I look at my favorite identity, I get nervous because that should be Hadamard dagger, obviously. But right, like that's kind of my mindset. So when I move on to thinking about a control knot, so I don't have a control knot button. What I have is this XX interaction. XX is sufficient to make control knot, but then you have to decorate it with these single qubit gates. So as we heard earlier, right, when we had ZZ, like you'd really like to make it ZX. So that's what these two Ys do. These two Ys turn this X into a Z. It gives me a ZX term. Then I have some annoying phases. I clean those annoying phases up with these two Rx rotations. But now I can do exactly the same thing. I just take the conjugate of C naught, and now I have C naught dagger. And what's neat about it is if I only have stochastic errors, the cost of running this in time and pulses and power is the same. So let's think about where it might be useful. So let's say I have some random quantum circuit, and I want to transform this into some small angle. First, I want to transform these X rotations to Z rotations because I know Z rotations are my friend. I apply that circuit identity. I basically add a bunch of Hadamards. And then I become nervous that these Hadamards and control knots should be inverses of each other. So I think, okay, well, this should be Hadamard, and this should be Hadamard dagger, and this should be C naught, and this should be C naught dagger, where I'm really just motivated, again, by my only rule. When I complete this, this problem here, actually, I disconnect this Z. And this is, I just want to say, when you're running a quantum simulation on a device which is doing transpilation or whatever, like this is one of the things you have to watch out for. Because the reason you put this circuit in here is probably to check for some error. And, sorry, I'm missing that part. Ignore that, sorry. But there's some, forget about it. So there's some examples where, this used to be connected here to look for something, but now it is just gone. But not here. Okay. So one of the reasons why I'm interested in this systematic errors, as I talked about in the last session, is I know these systematic errors really matter. So if I'm doing just single qubit gates with X and Y gates, in our system, fidelity is super good, right? I guess I could quit at 99.8%. But what I find interesting is if you put it into a model which assumes that the errors are stochastic, that the errors are always the same, or like the gates are always the same, such as we use pigs from Sandia, and you ask if applying SK1, which is a way to minimize error due to intensity fluctuation, it tells you, no, don't do it. You're going to go from 99.8% to 99.1%. But when you do it in practice, you actually improve the fidelity and you reduce the error. And it's not a flaw of pigsty. It's that pigsty assumes the gate's the same the whole experiment. But in reality, the gate's slightly changing as the laser intensity is slowly moving in time. So as long as this sequence here is faster than that slow oscillation, you get this improvement. Yeah, and that's just, this is just a different way to look at it with these polytransfer matrices, but it basically tells you, it's an amazing thing. So we use pigsty for both here and here to show the fidelity. And this is really just the prediction from this side. OK, so now what about the control knots? So here we have a classic example from a digital circuit where you have like a Z rotation, then you have this cascade of C knots. And then we compare numerically, we say, OK, numerically, let's have an over rotation and some under rotation. And we see that as long as the angle is small, which is also common if we're doing trotterization, doing the hidden inverses greatly increases the fidelity. However, if Z is close to pi, we're basically flipping the noise, which is intensity noise anyway. And so then we should just use our standard circuit, which is the purple dashed here, right? And so you could think about this actually in terms of a compiler. So you write down your regular circuit with C knots, and then you ask the compiler, which C naught should I turn into C naught dagger? And this, yeah, and I think what's nice about it is you don't really need pulse level control. You do need gate level control. And you need to make sure that when you send it off to the machine you're running on it, they aren't running some compilation in the background, which is removing all of the things you've added. but it can help. So let's look at an example of how this helps. So everything's pretty good in our system, so we usually have to repeat things multiple times to see noise. We just run this simple example here. Again, we have C naught and C naught dagger. Things could be even better because we should be able to cancel these 4 pulses here. But in this case, we don't cancel them because we want to try to show the effect without that extra gain just from cancellation. And then I think what's nice is we found something surprising. So in 2020, we ran this experiment. This is with C naught, C naught. For these curves, what you would like is you'd like for this green curve to go as close to 1 as possible, blue curve to be as close to 0 as possible, red curve to be at 0. And you'd like it to be centered around this angle, which is 5 theta. What's interesting is it works. We see much better contrast here. But this phase shift was unexpected. And it turned out to be due to this challenge of defining X. So Z is well defined. Z, your computational basis for most experiments is the energy eigenbasis of the qubits. It's defined by the phase of the clock. or right, it's just defined by those states. X and Y are always defined by the oscillation of that qubit relative to the clock. And then your 2-qubit gate, X, is also defined relative to that clock, but that, due to different experimental features, you might have some unwanted Z that comes in, which is different when you apply a 2-qubit gate than a 1-qubit gate. And so it turned out that this hidden inverse also helped that. And so later, so I think to me what's really nice about it is before we did this experiment, we didn't have an easy way to like double check this phase at very high precision. But now we can actually use this experiment as a way to make sure that our qubit X phase, single qubit X phase, and 2-qubit X are the same X, which has been pretty nice. Okay, yeah. So again, that's in the context of gates, and yeah, I'm going to shift gears away from gates. So any questions about that? I just want to show you how these Hamiltonians, even when people are giving you gates, the Hamiltonians are still there. And even if they only give you gate control, you can still cancel some things. Yeah. Yes.
Yeah, so I sort of have an experimentalist point of view of things. So if you have a strap of, or like a rope of ions,
Yeah.
right, your trap frequency, I imagine, changes along that line, correct? Or is the distance just way too small to the point that you don't really see any effect in that regard?
So when I have the chain of ions, the only thing that matters is, say, the motional modes. So the radial trap frequency from each ion is the same, but the motional mode splitting, we can see and dominate and resolve those motional modes. Yeah.
The phase shift we see here, is it because of the error in the detuning? Because like
Yeah,
okay.
basically. There's like a small, there's a slight difference in basically some Stark shift during those gates. And so here, like in these two experiments, like in this experiment, we like went all out to try to get the omega error as small as possible and have this be large so you can see the phase shift, and then vice versa there. Okay. All right, so I'm going to go back to some chemistry. So so all of my degrees are in chemistry, actually. That's why I'm a professor of engineering and physics. So when you think about real chemistry problems, maybe involving like photodynamics, you want to both think not only about like the energy of the electrons, but also vibrations between these various components. And this is true in biology, organic semiconductors, all kinds of stuff. So let's go back to like, this is just a different way of talking about the chemistry Hamiltonian we talked about before. Again, it just has nuclear kinetic energy, electron kinetic energy, nuclei electron attraction, electron repulsion, nuclear repulsion. And this is from my colleague, David Sherrill at Georgia Tech. He has actually great notes on quantum chemistry if you become interested, if you want to learn what CC-PVDZ means. So Born-Oppenheimer approximation, which I believe is the theme of the second Oppenheimer movie. I don't know. The idea is that the nuclei move slowly, electrons move quickly, and so we can do a separation of variables. And by doing that separation of variables, we assume the nuclei are fixed, we solve the electronic problem. And then after we solve the electronic problem, the electronic potential is something that the nuclei move around on. Most of quantum chemistry calculations for a long time, up until probably the last couple of years, have really focused on the electronic structure problem. So the last lecture of this school is going to be also about the dynamics problem, which is like super interesting. And as we talked about this second quantization, the mapping to Jordan-Wigner, mapping to these polystrings, is really all assuming the nuclei are just sitting still. And there have been, some nice work, different work looking at like hydrogen chains. This was an IonQ experiment that I was partly involved with, looking at water in this simple model that I talked about. And so that's been good. But chemists, have a long history of basically saying, okay, Dirac's right. This problem's too complicated. How do we simplify the problem so we can make some progress and try to understand what's going on with those materials? So one model, which is used in these photochemical things, is called the linear vibronic coupling model. Basic idea is the electrons live in states that have some energy. They can hop between the states, but they're no longer fermions. We've basically kind of, we've already kind of swept it under the rug. We then have vibronic coupling, meaning the energies of the electrons can change as these oscillators move. And then we have some oscillator energy. And you look at, as an ion trapper, you look at that, and you're like, okay, great. This is effectively my ion trap Hamiltonian. I should get to work on doing this. And so I just map the electronic states to qubit states, the vibrational modes to motional modes, and I take advantage of the all-to-all connectivity. So we...
Wait, real quick.
Yeah.
So those two sets of, so the size are the...
Size of the electronic states.
Okay.
Yeah.
And the A's are...
And the A's are the raising and lowering operator for the phonons, the motion, yeah. So in the context of, so in the context of, say, light harvesting, each of these chromophores will be one of the psi's. Psi A, psi J is hopping between chromophores. And then the A daggers are like local vibrations, but basically change the energy of the chromophores. Okay. Yeah.
Sorry, how do you actually promote the fermion to speed, like qubits?
Basically, because
Could you please repeat the question?
the question is, how can I somehow promote fermions to spins? So in that model, basically, I've already promoted it to like excitons. So I'm like basically watching this exciton hop around, and so all of the deltas have captured the information about the energy which is due to the fermionic interaction, and now I'm just watching the excitation move. Yeah, and it's just it's just an approximation. I'm just trying to make our lives feasible. So, I myself, I'm sure, am also guilty of it. So when you do quantum simulation, you often say, okay, look, we're working on this hard problem, hard to simulate, and you compare it against something which no one who actually works on the problem uses. Like you say, oh, look, we're beating diagonalization. And then you go talk to people who work on the problem with regular computers, and they're like, nobody uses diagonal, right? Come on, we use some couple of cluster method, we have tricks. So David Beratan is a professor of chemistry at Duke who works on chemical dynamics. So we went to David and we're like, David, we want to try to understand, is there a regime where we can do something with an analog quantum simulator which could beat your methods, not our methods, which would be terrible, but like what you do. And so what looks pretty exciting is that if you're in the limit where the coupling is weak, there's a lot of great like tensor network methods that are super good. And if you're in the limit where either thing is strong, it turns out Ehrenfest theorem, because basically if either of them is strong, there's like a basis which is easy to understand. And that basis, you can do a lot of fast perturbation theory, a lot of quick calculations. And it looks like the winning area is really to look at this in-between region, where from when I put on my perturbation theory hat, I think there's basically no good basis. I don't have a basis to do perturbation theory from. When I think about it, but to me it's just interesting because the electronic and vibrational dynamics, because they're kind of at the same energy scale, it just leads to a richer structure. And it causes trouble for the tensor networks because it basically blows up the amount of entanglement you have to keep track of. Okay. All right. So now I want to go back to this piece. So as you see, this term here actually creates exactly what I want, which is the spin term coupling to the oscillator. So instead of doing my usual 2-qubit gate, I basically want this piece to go to 0, and I want to set this piece to wherever I want to put it. I motivate it by this cartoon of a child on a swing. I think it's just, right, you just push the oscillator, you make alpha as big as you want. Okay, so today I'm not going to show you any experiments that get quantum advantage, of course, because you've heard about it already. But I want to talk to you about 2 experiments which show the kind of things you can do when you allow yourself to play with these bosons. So in chemistry, when a photon excites a molecule, the excitation has to somehow come back. Sometimes it happens by emitting light. Sometimes it happens to other pieces. But often what happens is it goes through this thing called a conical intersection. And it leads to like random outcomes here on the bottom. And this has been observed in all kinds of physical chemistry experiments. So in this physical chemistry experiment, they blow apart this molecule. And they can only explain the relative population of these outcomes by invoking these 2 conical intersections. So it's very promising. I've always been interested in like the most quantum things you can find. And so conical intersection also predicts that if I'm in the ground state manifold, there'll be a geometric phase. So this is the excited state potential, and this is the ground state potential. Because of this non-analytic point here, there ends up being kind of like a geometric phase, which means this wave packet will spread both ways and not show up on the other side. So in the 90s, when people were doing a lot of, just really getting into femtochemistry and looking at these photonic dynamics, these theorists suggested that you could measure it by looking at an interference signal in this femtosecond spectrum. And what they expect to see is a decaying cosine with a cosine on top, which could be many things, but that's what they expect to see. And then in their computer simulation, what they say is, okay, we're going to start with it's like oscillator displaced here. And then as it goes around the conical intersection, it doesn't reach here. It leads this kind of cut, which is due to the interference. And in molecules, this experiment has never been done 30 years later, because the timing is challenging, the orientation of molecules in condensed phase is tough, and of course the potentials can be quite complicated. But what's neat is in trapped ions, we can apply this. This is just 2 of the oscillators. This is just a spin-dependent force on the oscillators. And it leads exactly to this potential where I've kind of, in the adiabatic picture where the spins are set. And so we were working on this. Around that time, our friends in Australia also published a paper thinking about doing these conical intersections theoretically. Yes. So what we did is we just ran this. We basically start in these. This is the x and y position of 2 oscillators. So it's just a circle, quantum state. We then slowly ramp up these forces, and after we adiabatically ramp it up, and these are all calculations, it should form this nice C shape. If there's no conical intersection, it should form a donut. If there's a little bit of Stark shift, some unwanted z, 1 second, sorry, the c will actually rotate a little bit. And you can actually think of this as being you've lost control of that z. So they will average over each other and give you this donut. Yeah, go ahead.
How do we apply a spin-dependent force?
So we apply, just like in the gate, we apply a red sideband and a blue sideband at the same time. And that creates a spin-dependent push.
A red what?
A red sideband and a blue sideband.
Okay.
So we apply the remove a phonon and add a phonon, detuned a little bit usually, and it pushes it along. Now, what I want to point out is we do this in a trotter-like way. HX, HY, HX, HY, HX. And the reason we do that is it actually gives us better control of the factors in front, because we kind of just optimize it once, and then we just shift the phase so that we can apply, or we shift the frequencies, so it's the X oscillator, the Y oscillator, the X oscillator, Y oscillator. Yeah. Now the other thing we do, the other reason I'm really excited about this experiment is we basically did it at the same time as those hidden inverse experiments. And those hidden inverse experiments took place in a 5-qubit quantum computer. So we have 5 ions, but now we can pick normal modes in a smart way. So I'm going to pick V5 and V3 as my normal modes because they have low noise. It turns out the center and mass mode often has high noise because all of the electric field noise is far away from those ions. And so all the ions get kicked the same. The reason why we didn't pick V4 is by making the central ion be the electron degree of freedom here. There's no spectroscopic crosstalk to these other 2 modes. And then, because we have 5 ions, we just read it out with a second ion. So when we do this, so this is our experimental reconstruction here. This is just a different way to look where we kind of map around the cross-section to see that there's a dip in the center. What I really like about these experiments is, this is the picture which is in the paper. This is just a different one. I like this one a little bit better because here we had to rotate the C. There was a little bit of leftover Z error. Here we didn't have to rotate the C, but we had less contrast. And the student was like, I like the one with more contrast. It's fine, it's fine. But it's like something you can do again and again. And this is not quantum advantage, but it is an experimental implementation of a theoretical prediction that was not seen in real experiments until this experiment, right? Like it's kind of a weird, it's almost like experimental advantage. I don't know. That's too much. That's going to be the clip they put on the news. Anyway, so this team was really great. Chow is here, a postdoc at UCLA. I did it with Jungsang. Jacob's now at INQ. Ye is now a faculty at USTC. B. Chen, who did the hidden inverse work as well, is postdocing at Princeton in neutral atoms. Gloria, who's at UIUC, is also postdocing in neutral atoms. I also want to say that at the same time, our friends in Sydney also were able to show this. They had their simulation is way closer to like actually running the thing because there's one ion. That one ion has 2 modes. They use those 2 modes. And then the complication, from my perspective, is because they only have that ion to do the readout, it becomes more complicated because the ion should be super entangled to its motion. And then you still have to use that ion to somehow get the readout. But us having multiple ions allows us to get the readout a little bit easier. But they've done some really nice work this last year, moving away from this simple canonical intersection to try to make intersections look more like these real experiment, or like motivated more by real molecules. Ivan Kastelin, Tingray Tan. Okay, so now the other thing that came up in the coffee break was like, come on, Ken, you know nature's full of dissipation. Why are you just simulating Hamiltonians? Like we need some in real nature, like photosynthesis only works because there is dissipation, right? Like you need the electron to be trapped and energy to be harvested and all these things. All right, so let's think about how we can pull this off. So one thing you could imagine, it's kind of easy to do, or not easy to do, but you say, I'm going to use some of my ions in my chain just to cool down this mode so that I can set the temperature. So I'm basically constantly pushing it to some temperature. So I write down now, I have my usual spin operator. I have the spin connected to the force. I have the harmonic oscillator part. And then I have this cooling term. So I've added a Lindblad operator to do this cooling. And when you look at things like these light harvesting compounds, you actually have a continuous spectral density of noise, of modes. And then you see a ton of spikes. But the good news is, you know, you could capture most of this information with just a few, simplify it with just a few oscillators, right? So this all looks good.
Wait, real quick. Can you
Yeah.
go back to the Lindblad equation? So B is what is B here?
The same as A and the other things. So it's the creation and alienation operators of these motional modes. So there's a really nice theoretical result from Martin Plenio's group, which says, and it's kind of remarkable, which is if I have Gaussian states, so like thermal states or the ground state, this model, which has an infinite degrees of basically Bosonic modes, I can fake with one dissipative oscillator. And it's a little bit more formal than that. What it says is in the right picture, the 2-point Bath correlation function is the same. And that interaction is the only interaction in a Gaussian model which will interact with the spin. And since I make these 2-point correlators the same, I can simulate this with this. It's kind of amazing, yeah.
Question, like, fundamentally, if you're looking at this kind of speed motion model, it's kind of like already like full Hamiltonian, like kind of closed this way. On the other hand, you have like non-Hermitian like operators. So how can you have like a non-Hermitian stuff coming out of like a?
Yeah, so, okay, that's a great question. I'm going to repeat this question because I think I should repeat all the questions. But how does dissipation appear at all? I generally am like a Hamiltonians all the way down kind of guy. Hamiltonians are unitary. Where's the dissipation? But we know when I try to calculate for an atom, like what's the lifetime of an excited state, the dissipation somehow comes out of this integral. There's something about this continuous, something about this being continuous, leading to this spectral density, leads to, I guess, some non-recurrence, leads to it effectively being gone forever. Like you never come back. Does anyone have a deeper understanding of that? Do you guys know what I'm talking about there? Yeah, okay, go ahead.
Asking, so you're still kind of doing unitary, but your like system recurrences are not happening in your time scale that you're looking at or something
Yeah,
like that?
just because this is like, right, this like continuous, something about this integral just makes it, it's never going to happen. But it's actually, I really like that question. It's deep in my mind. And the way that I, again, explain it to myself is I know when I calculate, how do I calculate the rate of spontaneous emission, which is a dissipative process, basically happens because I've thrown this integral in somewhere, and I have some spectral density, and that spectral density pushes me that way. And so in some sense, this dissipation term here fakes this whole spectral density up to 2-point correlators. Okay. Oops, sorry. So in our system, we actually now in our system we have the sympathetic cooling. But when we were doing this work, we didn't have the sympathetic cooling. And so what could we do? Well, we could introduce dephasing. It's super easy to introduce dephasing. We're always trying to keep our clock perfectly online. We basically say, let's let the clock fluctuate around. Life's fine. These are very different noise processes. Like this one is a thermalization process. This one's phasing process. You can think of it as T1 type noise, T2 star type noise. But what's funny is if you only look at the second order correlators, they're still the same. And that's it was surprising to my student, surprising to me. I said, well, we know it just means the fourth order correlator matters. So in a Gaussian process, the second order correlator has all the information. For the dephasing process, all these higher order correlators will make a difference. So again, this is just saying the same thing. Everything's quadratic. Dephasing in this context is non-Gaussian because the Lindblad operators end up being quadratic in these oscillator operators. And as a result, we need to worry about these higher order correlators. But you could say, well, I don't have to worry about higher order correlators if I'm in the weak spin bath model. That's fine. So we did this with, everyone has left me. So Kuz, a postdoc at Lawrence Berkeley, working with Hartmut Hefner. Mingyu is a postdoc at Berkeley, working with Brigitte Whaley now. Hangai moved on to continue postdocing with Dave Baratan. Now we have 7 ions in the trap. Doesn't matter, we're just going to use one. We're going to use these different modes to do things. We have our oscillators as always. But what we can do is we can actually do 2 cool things. We can start the system in a thermal bath, in a thermal state instead of in like a fixed quantum state. And then we can add noise just by dephasing the operation of this motion. So these are just some plots of things we tried. So we could see that if we're looking at like acceptor donor population with this playing with the noise and the vibration. So if we have we try to start in the ground state, basically 0 temperature state, we see this nice oscillation and revival. As we increase the temperature, you see the revival damps out as you'd expect. We can increase, this gamma is like a fake damping term, which we're making with dephasing. And we can see that, again, the revivals damp out, the phase changes. Things seem quite reasonable. We can use the multiple ions to take advantage of these different modes to actually add different Lorentzian noises here. And then these numbers, this like wave number and this femtosecond number are obviously not what we do in lab. It's the simulated system would be a system working at femtoseconds, working these wave numbers. To me, the really good news was I was worried from our original paper. Our original paper, we tried to argue like what do we need to get to quantum advantage? And I was really worried about the motional dephasing of the trap. But it turns out for real systems with real dephasing noise, the motional dephasing is too small. Like we could just always have to add dephasing. It's not the critical point. This one was like a stretch where we're like, oh, can we look at something like ohmic baths, super ohmic baths, these things, more standard physics things? Answer is not really, because we don't have enough Lorentzian peaks to really map this. But over the point of near resonance, we can see these, we can map these different features and capture, again, the circles are all experimental data. The lines are kind of our theoretical predictions. And then this last one points out the difference between the second order correlations. So this vibrational assisted energy transfer is kind of a resonant process. It needs to borrow some number of phonons. So it has to be, so either borrows 1 or 2, which is the green and blue. But it can't borrow energy from here because it's just not resonant. If we turn up the temperature, we wash out the oscillation from the donor to the acceptor. And then I should mention that this is all, I lost a slide where like Hartmut-Hefner did a really early work on this vibrational assisted energy transfer. And we're just adding noise and dissipation and seeing how it changes. And then this one I like because it shows this emulating a T1 process with a T2 process. So again, the dots are just the experiment. The solid line is what you'd expect from an actual T1 process if we were actually doing the dissipation. The dashed line is what we expect from a T2 process. And then what you see is when the coupling is weak, you can actually effectively fake the T1 process pretty well with a T2 process for quite a long time. But if you make it stronger, then of course they have to deviate because they have different fixed points at the end of the day. And then at the same time, Guido Pagano's group at Rice, they did some really nice work with this tunable dissipation.
We have a way to convert this number n into actual temperature. So you're saying for different n's, you have the higher different temperature.
Yeah. So in our trap, the frequency of the modes is like a few megahertz. And the temperature is basically 2 times a few megahertz, which ends up, we go from a temperature of like 5 microkelvin to 20 microkelvin, some tiny change. But in the context of the thing we're simulating, you're basically going from kind of room temperature up to like maybe 700 degrees. Okay, so Zora is going to talk about different ways to look at nuclear physics simulations. And so I think one thing which is kind of cool is this spin boson stuff can also be applied to nuclear physics and particle physics problems and other high energy problems involving gauge fields. And there's this nice paper basically showing how to do with superconductors, followed by a nice paper. So all these plots here are from like ways to think about doing with superconductors and resonators, and then a follow-up paper on how we can do the similar things using trapped ions. My colleague Norbert, he actually looked at just using the bosons not as directly as part of the simulation, but just as a way to generate some entropy. So you basically set up the bosonic modes, couple them, entangle them with the ions, and then you throw them away. Like you never look at them again, which means your spin system now has some effective temperature. And they used it to look at these different, these gauge fields, SU2, kind of simple models. And so I'm super excited about this as like a place where analog simulation can be pretty useful, partly because it does look like there's a narrow path to potential quantum advantage for problems people care about. That's exciting. The second thing is that when you think about what it takes in terms of qubits to map the bosons to spin operators, it's pretty expensive. So if the quality of our system is good enough that we can use these bosons relatively, use them well, then I think it's a huge savings. I'm not going to talk about it, but we actually got kind of this Gaussian to non-Gaussian noise kind of gets me because to me, dephasing is like, in my mind, T2 is easier than T1 because T2 is just shifting energy levels. T1 is like energy leaving. But it turns out so many of our methods, numerical methods classically, are so efficient with the Gaussian things that when you add dephasing noise into those methods, they just go crazy. And so we started to think about how you could use that for a phase transition, but also I think that's another place where maybe will help us towards quantum advantage. And so then I'll just wrap up before questions. So pretty much all the work I talked about, all those people are gone. We have new people. There's Dimitri, who Jacques walked in. Lost him. We work kinds of things. I would say probably half the group works on error correction at present. But this work really, we're thankful for the funds for the robust quantum simulation. Duke Quantum Center is busy and growing. When I showed up, it was just Iman and I and Jung Song and Robert, and I guess Henry. And now we have all more people. I heard that Yutong and Difang were visiting last week. Is that right? They're great mathematicians. I am currently leading, it's called the National Quantum Virtual Lab. The way that I think about it is it's like building a telescope. So when you build a telescope, you don't really build it for yourself. You build it for everyone else to come and use the telescope and look at stars in space. And you have some target in mind, like, oh, I'm going to build this telescope to look at this galaxy. But then people will come and point it all over the space. And so we're in the design phase to build basically a big academic ion trap quantum computer, which will generate a lot of users. And again, I think our plan is to have the first one kind of online in 2030, which is further away than 2028. But these things take time. And I'm happy to talk more about it. So yeah, thanks for your time. Love to answer more questions.